things from the last hour? Some of you, some wanted to see in a little more detail. So if I have a blow up, so if I have a smooth center in X, and X tilde is the blow up along Z of X. Let's write it this way. Let's call this F. We claimed that R F lower star OX tilde is OX. And here I want Z and X to be both smooth. Otherwise, what I'm saying is false. So in my mind, like morally to me, this is, you could use Grauert's theorem and say that the cohomology of O along the fibers is just one. Like the fibers are either points or PNs. So the cohomology of O on the fibers is always just 1 and then zeros. And so R0 F lower star OX tilde is OX, and the higher push forwards are bigger than 0 F star OX tilde is 0. But of course, you can't really use Grauert's theorem like that because this map is not flat. So, and if you try to use that same argument in other situations, you'll get yourself in trouble. So that's a mnemonic rather than a proof. One way to see it is from Zariski's main theorem, or Sasha was advocating a simpler proof that's like the same techniques but less. But you know, the base is normal and the fibers are connected, and so there you go. For this, we can do a little induction. You know that F is a projective morphism. You know, it comes about through some Proj construction. And, well, let's induct. I have OX tilde onto OE, and I'm going to do this fully because it's good to write OE of E and OE of minus E as many times as you can. So you get used to them. O X tilde of minus E. And E is, you know, E over Z is a PN bundle. The fiber is PN. And so it's really true that RF lower star OE is OZ. There you really can use Grauert's theorem. Think about the cohomology of PN of the fibers. So here we have OZ. So I want this is OZ. This is OX. I want this to be OX 0 and 0 and 0, and so this will be IZ 0 and 0 and 0. So that's the answer. But this part we know. This we want. We want this to be 0, so this is what we need. That these are all 0. And so we'll keep inducting. So we can go O of minus 2E, OX of minus E, OE of minus E. And this is OE of sorry, this should be minus E of 1. It's well, if Z is a point, then E is a Pn, and it's a P and minus 1. And it's really O of 1. It's the relative O of 1 for E when you regard E as the projectivization of the normal bundle of Z. So this has This has no higher cohomology. And here we want this to have no higher cohomology. And so this, we need no higher cohomology. And so you induct on this like this. So what we need to show, so we should show that the higher cohomology of OX of minus NE vanishes for n much bigger than 0. You can, the next one's going to be O minus 3, E, O minus 2E, OE of 2. You know, O minus 4, E, O minus 3, E, OE of 3. You can keep making this argument forever. But this, well, OX of minus E is the relative. This is OF of 1. When you construct F as a proj. And so from the relative version of Serre's vanishing theorem, you know, when you twist this way up, then eventually this will have no higher cohomology. So you're okay. So, well, I guess Ri. Oh, sorry, am I writing? I wrote cohomology. I meant this has no higher push forwards. So we want, here we want, you know, higher push forwards. And so here we need no higher push forwards. I wrote cohomology, but I meant higher push forward. So we're okay. So it's relatively ample. Right. So if you haven't seen that, now you've seen it. And you have a little more experience messing around with these exact sequences. Right, so where were we? We stated Bailenson theorem that on Pn, you have this full exceptional collection of line bundles. And the proof, the sketch of the proof, was that, well, first of all, we saw that it was exceptional. Then we could generate all the points with those things. And so its orthogonal is 0. And then I'm going to prove to you either later this hour or in the next hour that so IOU if you have an exceptional collection, E1 up to En, and its orthogonal is 0, then E1 up to En is essentially that everything in the derived category is isomorphic to something generated by those guys. I'm not going to do that right now. And you have an exercise to show that instead of generating all the points, it's enough to generate an ample sequence of line bundles. Actually, I ask you to generate the sequence going in both directions, but you only need one direction. So you can figure out which direction you actually need. Okay, so next, there's a theorem of Kapranov that I'm not going to prove. On Grassmannian Kn, let's let U inside of O of the Grassmannian to the N be the tautological rank K subbundle. So it's the bundle that at a point of the Grassmannian gives you the subspace of K to the N that point parameterizes. If you're in projective space, U is just O of minus 1. And then the claim, the theorem, I'm not going to prove, then the Schur functors lambda of U dual for lambda, a Young diagram fitting in a what size a box, contained in a k by n minus k rectangle, form a full exceptional collection. So to show that it's exceptional, you do a ton of calculations with Borel-Weil-Bott to find cohomology of these homogeneous bundles. And then to show that it's full, I guess you could, well, there are many ways to show that it's full. But that's a direction you can go with that. It's also true of flag bundles. Yes?
So the definition of exceptional collection depends also on like an order.
Yeah, so there is some order that you can put these things in. So that, yeah, I agree. Yeah, no, that's a good point. But you can see in if we're on Pn and U is O of minus 1, so U dual is O of 1, your 1 by n minus 1 rectangle is going to give you symmetric powers of O of 1. So this is really a direct generalization of the Beilinson exceptional collection. Next, let's do, so next, here's a proposition on x tilde, which is the blow up at a point of P2. Our exceptional collection, which was OE of minus 1, O of H, O of 2H is full. And you have an exercise to find a different full exceptional collection on well, a couple different exceptional collections on this x tilde. So what do we need to do? We need to generate all the points. O points for every p in x tilde. Well, right, and let's draw here's x tilde mapping down to P2, and there's E. So if I'm at a point here, if P is not in E, then it's the pullback of some point downstairs. And then OP is F upper star O F of P. Right? I could write LF upper star if you want. Right? F is just an isomorphism out there. Right? And so for O F of P, we have a Koszul complex. O minus 2, O on P2 of minus 2 goes to O P2 of minus 1 squared goes to O P2 goes to O F of P. And so when you pull that back, you get OX tilde of minus 2H, and you get the idea. And so these three are enough to generate all the points that are not on the exceptional divisor. On the other hand, if P is there, and if P is the center of the blow-up, then what can we do? Sorry. If P is in the exceptional divisor, then f of P is the center of the blow-up. And so yesterday in the exercises, or 2 days ago, you saw that LF upper star of O f of P has, well, Li, this has two cohomology sheaves. One is OE if I is 0, and OE of -1 if I is 1. I was preparing this and I thought, man, I don't want to do this calculation. And then I remembered that I'd already made you do it. And so what can we do? So we have a cone for, right? So of course, so this we can generate with O minus 2H, or O. Oh, sorry. Or we could, I made the same mistake I made with Bailenson earlier. I can twist these by 2H. And then twist OP of 2H is OP. So that doesn't matter. So these we can generate with O of H, O of 2H. This complex with two cohomologies I can generate with those three. And so what can we do next? Now we have OE minus 1 around. Right, so we have a map from OE minus 1 shifted by 1 to LF upper star O f of P. So I think Sasha explained very early on that a complex always has a map to its last cohomology and from its first cohomology. So I have this, right, I'm generating with those 4 objects. I can generate this one, and I already had that one, so I'm going to take a shift of it, and I'm going to take this map. And what's the cone? Well, we get the long exact sequence in the cohomologies of the cone. Here I'm going to have H minus 1 is going to be OE minus 1. Here I'm going to have OE minus 1 and OE. By construction, that's going to be the identity. And so in the cone, I'm just going to get 0, and I'm going to get OE. So the cone is OE. I know I'm reaching way back to Monday and Tuesday for this kind of thing. Right, you computed that this thing has these 2 cohomology sheaves. It has a map from its leftmost cohomology sheaf, which is here, and you take the which we already had. So now you take the cone, and you get a long exact sequence of cohomology sheaves from that. And so you can figure out that the cone is quasi-isomorphic to OE. Right? If I have a complex that has only one cohomology sheaf, then it's quasi-isomorphic to that simple complex. It's just zeros, OE, and zeros. And so last, we have a short exact sequence, OE. So we can generate OE, and then we can take this, because E is just a P1. And so now we've generated all the points in sort of a lot of steps. There are slicker ways to prove this kind of thing, but I think it's good to get down and get your hands dirty with how the derived category works, how you really calculate. So I still have this IOU that's showing that it generates all the points is enough. Questions? Yes? Right. So, yeah, that's good. That's a good question. So, OF of P is generated by OP2 of 1, OP2 of 2, right? Because it's a point in P2. So that's the Bailenson collection. And there's the argument again. And then you pull that back. Right? If this thing was gotten by taking cones of those, then you pull back, and now this thing is gotten by taking cones of those. I guess I'm assuming that you know that the pullback takes cones to cones. Right? So I guess this is something we discuss tomorrow in a lot of detail. That all these derived functors take cones to cones. Other questions about that? Let's see an exceptional collection that is not full, right? So let's take a quadric fourfold in P5, a smooth quadric. And we know, so the canonical bundle, omega P5 is O minus 6. So omega Q is O minus 4. And so we had an exceptional collection, O of 1, O of 2, O of 3 is exceptional. But I claim it's not full. And what we'll do, we'll exhibit some S in O up to O of 3 that's orthogonal to these, that's non-zero. In this case, yes, yes, I'll say that at the end. In this case, you can add something. In general, you can't hope to add something. Like if you have but for quadrics, you can do it. This is another theorem of Kapranov. And the reason I'm going to do it this way is I want you to see the formula for, well, I want you to see the techniques that we use along the way. Right, so let P inside of Q be a plane. So a quadric 2n-fold contains two families of pn's. You know that a quadric surface contains two families of lines. It's also true in higher dimensions. A quadric fourfold contains two families of planes. And let's consider OP of 1. So is it orthogonal to these 4 line bundles? Well, our Hom from OQ of 3 to OP of 1, our Hom on Q, of course, not on the ambient space, not on P5. This is R gamma of OP of minus 2. Which, if you remember the cohomology of line bundles on Pn, is 0. And similarly, OQ of 2, and we're going to get OP of minus 1, and this is 0. So far, so good. We have no Homs from this or from that. But of course, R Hom of OQ of 1 is R gamma of OP. And the cohomology of OP is, this is, okay. There is one map from OQ. Oh. And you know exactly what it is. It's just the usual restriction map, twisted by 1. And what's the kernel? This is the new thing. I'm going to take, right? OP of 1 is not orthogonal to OQ of 1. But I'm going to make it orthogonal in the following way that you're going to see more and more. So what's the kernel of that surjection? If I didn't have the 1s there, I see you're all feeling shy. This is the ideal sheaf of P and Q. Twisted by 1, right? Functions on Q that vanish when you restrict them to P are just, that's the ideal of Q. And I twisted by 1 everything because I can. So now, so I claim that the ideal of P and Q twisted by 1 is now orthogonal to O of 1, O of 2, and O of 3. Right? If I take X'd from any of these 3 to here, I get 0. So why is that? Well, first, if I take X'd from O of 3 to this, from this exact sequence, there were already no Homs from O of 3 to this or that. No X's from O of 3 to this or that, and so there are no X's to this new thing. We haven't messed that up. Similarly, there are no X's from O of 2 to this or that, so we haven't messed that up. OQ of 3 to OQ of 1 or OP of 1 equals 0. So the same for this cone, I. If you want, you can say this thing, well, up to a shift, this thing is the cone, this ideal sheaf is the cone of this morphism, and the orthogonal to O of 2 and O of 3 is closed undertaking cones, because you have that long exact sequence. So if 2 of them were orthogonal, then the third one is orthogonal. X from OQ of 1 to I P over Q of 1. This will be more interesting So we're going to take x from OQ of 1 to these things, to that short exact sequence, to the short exact sequence above. And what am I going to get? I'm going to get 0. X from OQ of 1 to OP of 1 we already calculated. This was k, 0, 0. X from OQ of 1 to OQ of 1 is also k, 0, 0. And this, by construction, this is an isomorphism. You take the identity map from OQ of 1 to itself, and then you restrict, and that's the map that it has to be. And so this has to be all zeros. So we took OP of 1, which was already orthogonal to these two, and we projected it into the orthogonal to that third thing and came out with IQ, IP of 1. So this was X. That's probably totally illegible. It was really helpful that OQ of 1 was exceptional, that its self-x's were boring. Okay. Yes?
So we're applying this concept to that short exception.
To this.
Shouldn't the arrow be going the same?
Oh, right, yeah. Very good. In the exercise, they're all backwards, but in this, they're all forwards. And so, how are we? We stop at quarter till. So now we're orthogonal to 3. Let's go one more. Now, x from from OQ to I P over Q, P and Q twisted by 1. Well, you know what HOM is? Sections of the ideal sheaf twisted by 1. That is linear forms on Q that vanish on P. Right? H0 of I P over Q of 1. This is linear forms on Q that vanish on P. And you know P is cut out by 3 linear forms. And the linear forms on Q are the same as on the ambient space. Right? Because when you take that quotient ring and you kill a quadric, you're not killing any linear forms. So this is K cubed. And then, well, I claim it's 0, 0, 0, 0. And the reason is if you took cohomology of that long exact sequence, see, maybe that's the best way to see it, of that short exact sequence. So if I take cohomology of this, I'll get 3, 0, 0. Here I'll get 6, 0, 0, 0, 0, 0. Because linear forms on the quadric are the same as linear forms on P5. And here you get the 3 linear forms that vanish on that plane. Or that, yeah. Great. And so we'll play the same game again. So we have a map from OQ cubed to the ideal sheaf. And it turns out to be surjective. And I'm going to declare the kernel to, I'm going to call it S for spinner. What it has to do with spinners is a long story. Right, so now for the same reason, this all right? Are you all falling off the horse, or are you? Let's think about why that map is surjective. It's because, because the ideal of P is generated by these three linear forms. Is the reason. Is there any better reason? No, that's the best reason. The ideal of P is generated by these. That's what it means to be surjective as a map of modules and thus of sheaves. Great. So we have this S that fits here, and I claim now I'm going to keep that there. So I claim that S is now orthogonal to O, O of 1, O of 2, and O of 3, all of them. Right? This was orthogonal to those three. O was orthogonal to these three. And this was orthogonal to those three. And so this is as well, by doing the long exact sequence. On the other hand, Arham from O to S is, X'd from O to S. This is the cohomology of S. And we just figured out this thing has cohomology 3, 0, and 0. This one, this is 3 copies of OQ. Right? And OQ was exceptional, so now we get, instead of 1, 0, and 0, we get 3, 0, 0. And the way this evaluation map was exactly designed so that that's an equality here. We said that this ideal sheaf had 3 sections, and this map is those 3 sections. And so this thing has no sections. And now what's the fastest way to see that S is not 0? Oh, yeah, okay. I was going to take cohomology. That's much better. I was going to twist by 1 and see that it had sections. But no, this has rank 3 and this has rank 1, so rank is 2. So this is, okay, end of calculation. It is a vector bundle. Yeah. You know that Hilbert's syzygy theorem says if I take high syzygies of we're in a fourfold, so if I take some 4th syzygy sheaf, then that will be a vector bundle. But actually, that plane was codimension 2, so I only have to take a 2nd syzygy sheaf. So S is actually a vector bundle. And you can there's a long thing in the last exercise, which is a bit ambitious, but I invite you to have a look at it. S is actually exceptional. S is exceptional. It's called a spinor bundle. And there are many ways to construct it. You can construct it with Clifford algebras. You can say, well, the automorphism group of the quadric is some orthogonal group, And the stabilizer of a point is some smaller orthogonal group, and I take the spin representation of that, and the associated bundle is this. There are many ways to construct S using make it more clear that it's a spinor bundle, that it deserves that name. But I like this way. So the process that we've learned is we had some exceptional collection. We had some random object, right? OP, by the way, is not exceptional. At some point, I think you need to compute its self-Xed algebra, but in the exercise. But you know that plane moves in a 3-parameter family, and so it has some self-Xed 1. So it's not exceptional. If it moves, then it's not exceptional. Whereas S, it turns out as you move P, S doesn't move. And Kapranov will tell you, given sort of infinite time, we could prove this by these same methods. But Kapranov. Take a plane from one family and a plane and another plane. Let's put the plus down. From the two families of planes on Q, and form S plus and S minus. Then S plus, S minus, OQ, OQ of 1, OQ of 2, OQ of 3 is an exceptional, is a full exceptional collection. So in particular, there are no HOMs, there are no X's between the two different spinor bundles. Kapranov proves much more than that. He considers smooth quadrics of any dimension. So to make the spinor bundle, you can either play around with representation theory, or you can take a maximal linear space and take some high syzygy bundle of it. If you're in a quadric 2n fold, you're going to have to go n steps rather than just 2 steps. On an odd dimensional quadric, there's only one family of maximal linear spaces, and so you only need one spinor bundle. So there's a whole story there. That's a lot of fun that we might continue to meet along the way. And while we're here, this is well, I'll call this the Kuznetsov philosophy. So on a Fano variety X with, let's write omega X as O of minus K, where O of 1 is some vector bundle that's not, there's some ample line bundle that's not a multiple of any smaller line bundle. The exceptional collection O of 1, O K minus 1 is never full. Unless Unless X is Pn. And the orthogonal this orthogonal is always, well, okay, this is not philosophy, this is just a true fact. This orthogonal is always geometrically interesting. Okay. Well, for a quadric, it was just two two exceptional objects that were orthogonal to each other. It looks a bit like the derived category of 2 points. I'll come back to that comment later. But these spinor bundles are quite geometrically interesting. For higher dimensional, or for bigger hypersurfaces and complete intersections, that orthogonal becomes more and more interesting. I hope we'll have time to meet if x for example, you have this Bondel and Orlov thing that we'll see how much we can say about this. If x is the intersection of two quadrics in Pn, in Pe5, so x is a threefold, then O up to, well, O and O of 1 perp is the derived category of a genus 2 curve. Depending on how we get on, we might have time to talk about that. Kuznetsov, if x is a cubic fourfold, then take as many line bundles as you can and look orthogonal to this wants to be the derived category of a K3 surface, and it only sometimes is. And he conjectures that that's connected to the rationality of the original cubic. So these are the best examples, but there are other ones too. And next week, this Orlov theorem that we're going for is to relate this orthogonal for hypersurfaces to matrix factorizations of the equation of the hypersurface. So that's somewhere we're going in the long term. But even for just a cubic surface, a cubic surface is the blow up of the plane at 6 points, right? And so you already have an exceptional collection with those 3 line bundles from the plane and six things from the exceptional curves. So you could think about that example. There you just, maybe I'll write it. If I have a cubic surface, then omega x is O of minus 1. So we just want O perp is generated by O of the first exceptional divisor minus 1 up to O E6 of minus 1. And then I could do O minus 2H and O minus H. But so if it has a full exceptional collection, it's in some sense not that exciting. But, okay. That already has a lot of geometry in it. Okay. So I have 10 minutes to talk about whatever I have to say next. Let's do that. So instead of exceptional objects, now we want to talk about semi-orthogonal decompositions. And we'll get started, and then we'll resume after lunch. But all this stuff that we did will be relevant. So definition. A full subcategory A in D of X, which I want it to be not only full but closed under shifts and cones. So I want it to be a triangulated subcategory. is admissible if the inclusion A into d of x has left and right adjoints. And again, this is purely a thing about triangulated categories, so we don't have to be in d of x, but why not be? So let's have examples and non-examples. So examples. So the image of a fully faithful functor from another variety. And the reason is that the functor is induced by a kernel, and so the adjoints are given by Mukai's formulas. All right, if we have a functor that's induced by some kernel, we know the left and right adjoint are induced by the dual kernel tensor, some canonical bundle on either side with a shift. You're saying, does the inclusion not always have left and right adjoints? Is that the? Yeah, we'll come to that. Yeah, that's. And by the way, if I just had a functor that wasn't fully faithful, right? Then that map would still have left and right adjoints, but it wouldn't be identified like. The image of that functor would not be equivalent to the original thing, right? Fully faithful means it's an isomorphism on all the Hom sets. So it'll give, you should think of a fully faithful functor as giving an equivalence with its image. I'll say something more about that in a second.
So if it's just a fully faithful functor,
You have to assume that it has left and right adjoints. I guess and indeed in Orlov's original business, he assumed that the fully faithful functor had left and right adjoints, but then I think Vandenberg went back and proved that he didn't need that. So there's some fancy stuff that's hiding in there. Should I do the non-example first? You guys seem more excited about the non-examples. Let's do the non-example. Let's let C be the subcategory of d of x generated by skyscraper sheaves. So I have all my skyscraper sheaves around. I'm allowed to take cones between them so I can get sort of sheaves with finite support. Why does this inclusion not have adjoints? Then C perp is 0, as we've seen, but C is not all of d of x because because everything in C has finite support. Okay. Well, I want to prove for you, either now or later, that if I have an admissible subcategory whose orthogonal is 0, then it's the whole category. So since you asked, I was going to do this after the break, but I'll do it now. Proposition: if A in d of x is admissible, and A perp is d of x, or A perp is 0, then A is d of x. So let's do that now and then break and do exercises and eat lunch. So the proof is we let I be the inclusion, and let's have the left and right adjoints be called L and R. The inclusion, and these be the adjoints. Where have I got this? And let f in d of x be arbitrary. I'll call it E, be arbitrary. Then we have, you notice that E is in A perp if and only if R hom from the inclusion of something in A, IF to E. This is, sorry, let me make this a small e, so my functors can be big and my objects can be small. Is 0 for all A in A. And this is R hom from A to right adjoint of E. And by Yoneda, this happens if and only if the right adjoint of E applied to E is 0. So A perp is the kernel of R, and perp A is the kernel of L. I'm sorry, I'm over time. Can I pick? I hate to run another minute long. Can I pick this up after lunch? I'm going to pick this up after lunch. If you want, you can think about how to finish this. It's only like one, oh, fine, it's only one more line. You have the unit of the adjunction like this, so you get a map from E to RFE. And no, we'll do it after lunch, you're right. That spinner sheaf business is tiring, right?